Hi, welcome to our last lecture in the Advanced Combinatorics sequence for the 2021 or 2020 would-be Stellenbosch Math Camp. And I'm going to talk to you about game theory today. Last topic. Now, for game theory, there's a free textbook, completely legally. The author, who's a professor at Carnegie Mellon University, has put everything up on his website, and you can spend as much time as you want going through that and learning this material in a lot more detail. But let's start with the warm-up problem. I've got a pile of 22 stones, and two players are going to take turns removing stones from it. And at each step they're going to either take away one or two stones. Okay? And if you take the last stone, you lose. Okay, it's poisoned or something. Okay, so do you want to go first? Okay, and the answer turns out to be no. I take one, you take two. Or if the first person goes, if you let yourself go second, the first person, if he takes one, you take two. If he takes two, you take one. Either way, 3 stones disappear. Go from 20 to 19, and then from repeat the strategy. He takes 1, you take 2, he takes 2, you take 1. You then go to 16, 13, 10, 7, 4, and 1 stone, and he has to take that and he loses. Okay, well, 22 is kind of arbitrary. Let's talk about which stone sizes you might want to go second for. Well, firstly, 1, 4, 7, everything that is 1, 1, 3, you want to go second. You just say, okay, you go first, you do the opposite thing, you take them away 3 at a time, eventually you give him 1 stone, it's his move, and he loses, so you win. Now, if it's anything else, if it's 0, 1, 3, you can take away 2, and now you're effectively playing second in a game which starts with 1, 1, 3. So, and he can do that to you too. So therefore, you do not want to go first. You do not want to go second when it's 0, 1, 3. You want to go first, and if it's 2, 1, 3, same argument works. Just take away 1 instead of 2. You do not want to go second on any of the other numbers. So 0 or 2 by 3, you want to go first, 1 by 3, you want to go second. Okay, and the important idea here is once you've found some winning positions, anything which can move to them, or some winning positions for the second player, anything that can move to them for the first player is a no-no. Right, those are just no longer second position moves. Okay. So let's move on to Nim, which is a similar game. You have n piles of stones, and each move you can take as many stones as you want away, but only from one pile. And here, taking the last stone wins. Another way to think of this is you lose if you can't move. Okay, so you can't move, you lose, therefore if you can take the last stone, the other guy can't move, he loses, you win. Okay, so we're going to split these positions into first player wins and second player wins positions, and we're going to talk about which positions are first player wins, which positions are second player wins. Okay, well, if we've only got one pile of stones to start with, the first player wins, he just takes them all. Okay, the one exception to that is if it's an empty pile. Okay, so now let's look at the 2 pile case. Okay, if they're both empty, quote unquote 2 empty piles, 1 empty pile, 5 empty piles, all the same, second guy wins because the first guy just loses right away. But anything else where one of the piles is empty is the one pile, is really one non-empty pile, and the first player just wins. Okay, so the next case we care about maybe is this 1-1 case. Well, what can you do in the 1-1 case? You can just take away 1 stone, you move to here, and that's first. He's going to win. You don't want that, so that's a second. Sorry. The 2, I'll take 1 away, he'll have 1, he'll take it. I can't move. So I do not want to do that. A second player moves. I want to give him 1-1, and then he takes 1 away, and I take the last 1, and he loses. Okay, anything where one of the piles is 1 and the other one's bigger, the first guy wins. Okay, and the reason is if he has a 1-7, he gives you back 1 and 1, taking 6 away from the big pile, and there. But now what we've got is this notion of, hey, you can move anywhere in this direction, anywhere in this direction, and if they're all firsts, second's going to win, otherwise first guy's going to win. So 2-2, same story. I can either go to 2-0, he's going to take it away, I lose. I can go to 2-1, he's going to go to 1-1, and that's really all I can do. Okay, and again, anything bigger, 2 and 7, he can go to 2 and 2. So these are all firsts. Okay. So if you can go to a second, the first player is going to win, and if you can't, second player, you actually are the same player going to win. And we repeat this, and it turns out the winning strategy here is to get to n and n, or to give him 2 equal piles, and whatever he takes away from one, you just copy on the other. Right, and anything else than that, if you give him anything else, he can do that to you. So that deals with the 2 pile case. So let's deal with 3 piles. And because I can't do a 3D table very easily, I'm just going to start with 1. With a 1 in the first place and an X and a Y. Okay, so if it's empty, the first guy's going to win, because, well, it's 1 stone. I take it away, I win. And here, this is the 1-1 stone, so is this. They're seconds, they're all firsts, and so on. Okay, in really exactly the same way. Okay, this one is a 1 because you can sort of think of it as there's a second in 0 to 2 underneath it. Okay, but this one there's not, and even below it, and we end up getting this thing sort of swapping in every block of 2. Okay, that's quite interesting behavior already. And for 2 it looks a little bit stranger. You have this and that. You have still got these two blocks, but now they're also flipped here. Or now they're flipped in groups of 2 instead of in groups of 1, like they were before. Right, so here with 0, with 2 piles, these things were on the diagonal. Here they flip here. In the 1 pile, these 2 swap. And what happens in the second one is they're still diagonal, but as blocks of 2 they're flipped. Okay. And to do a few more of these, if you want to do that, pause the video, do the 3xy case, see what you get. Do the 4xy case, see what you get, see if you can find a pattern. Okay, welcome back. So you look around and it seems like it's the XOR sum. Okay, where of the numbers involved. And if you don't know what XOR sum is, I'm going to explain it now. So XOR sum, you write a number in binary, so 13 becomes 1101, XORed with 112, which is 1100, and I'm going to take XOR, which is exclusive OR. So XOR of 1 and 1 is 0, XOR of 1 and 1 is 0, XOR of 0, 0 is also 0, and XOR of 1 and 0 is 1. Okay, so this is binary addition mod. This is addition 2 on the bits. okay, on the binary representation. There's another example, 13 and 6. 13 stays the same, 6 is 4 plus 2, and we get a 1 in the first place, and we get a 1 in the units place, and zeros between. That works out to 9. Okay, now in order pardon me. Okay. So we think it's XOR, and XOR not just for 3 but for n cases. Okay, and if we look before at the 2 pile case, it really does look like XOR. Okay, and it's not too difficult to prove. It's well, particularly for the 2 pile case, it's not too difficult to prove. It's going through a bunch of cases, and that turns out to be all we need. So let's talk about something called a sprung and Grundy function. Okay, Sprung and Grundy both came up with this theory entirely independently. Okay, so any perfect information alternating game. So what does that mean? Alternating, I make a move, you make a move. I make a move, you make a move. Chess would be an example. There is a little bit of a caveat here. In fact, so it's not any perfect information alternating game. Perfect information means I can see everything. So chess, I make a move. So alternating means I make a move, you make a move. Perfect information is I can see everything, you can see everything. So poker, for example, is not perfect information because I can't see your cards and you can't see my cards. Chess is perfect information, but you also need no draws. And you also need to be able to make the same moves on the board. So I can move my pieces in chess, you can move yours. You don't have the same move set from the same position. But nonetheless, if you have a game with perfect information alternating, you can move on the same pieces and no draws. For every x we have the Sprung Grundy function, which is the smallest non-negative integer not taken by a successor. Okay, so you look ahead at all the moves. The terminal states of the game don't have successors, so they have Sprung Grundy number 0. The states which every other state, you look at what moves you can do, and you go, okay, I see a 0, I'm not a 0. I see a 1, I'm not a 1. I don't see a 2, I'm a 2. Or you see absolutely nothing, or you see a bunch of terminal states but none of them are 0, you go, oh, I'm a 0 too. Okay, so that is the Sprung Grundy function. Now, it turns out seconds, which means things, if I give you this position you've lost, are exactly they're not exactly. Yeah, they're exactly the places where you win. Okay, because if you're at a 0, by definition, if I give you a 0, you're at a position that's 0, you look at everything you can move to. Well, it's 1 or higher, you move to something that's not that, you give it back to me and I can go to 0, because if you're a 4, that means you have a 0. Okay, if you didn't have a 0, you'd be a 0. Okay? So I can always force things. If I give you a 0, whatever happens in the next sequence of your move, my move, I can give you a 0 again. Eventually things are going to terminate, which I think is another condition I should have mentioned up front. And when finally it'll terminate, same rules as NIM under normal circumstances, so it be sticking on the zeros means a win. And if I ever give you something which isn't a 0, you can get to the zeros, so I will lose. Okay? So some version of Nim is contained in this game. Okay. Really, one pile Nim is contained in this game. Now, if I have two of these games played at once, in this way, I pick one to make a move on, and I move, and then you pick one to make a move on and you move. That's very much like two pile Nim. The first game being my pile, the second game being your pile. Okay, so now 7 pile Nim, for example, is 6 pile Nim and 1 pile Nim. And 6 pile Nim is 5 pile Nim and 1 pile Nim and 1 pile Nim. So that's how we're going to get to infinitely many piles from a single one. Okay, so the essence of 2 pile Nim is contained in 1 pile Nim. Okay, we'll induct. And I'm just going to give you another example called Laska's Nim. So Laska was a world chess champion. The story about him where he was on a ship cruise after he'd retired, and there was someone who said, had a board, and said, not knowing who he was, why don't we play? Sure. Okay, and look, well, do you play? Oh, a little. This was true. Every 3 years ago he played a tournament. I think he might have said once every few years. And okay, well, says the guy, why don't we play it? I'll give you a queen. I'll play without a queen, and if you beat me, well, we'll move down to rook and we'll match up. Laska says okay, and so this guy's playing a world champion down a queen. Laska decides to lose, and then he decides to lose again, and he says to the guy, it seems like there's some advantage to not having a queen. Maybe because this king has a little bit more space. Let me play without the queen. Well, the guy's very, very tries to convince him there'd be no point, but eventually says, okay, you were polite to me, so I'll be polite to you. Well, let me show you this. And he gets obliterated a few times, and starts walking around very concerned about how chess works until someone told him, yeah, that's Laska. But in Laska's Nim, you can do all the usual moves you can do in Nim, but you can also split. So if you've got a pile of 10, you can take 1, you can take 2, you can take 3, you can take 10. You can also split it into 2 5s, or 4 into 6, or a 3 into 7, or so on. Okay, so let's work out this g of x, the Grundy function for x. And we only need to do it on a single pile, because that will then be enough to... if we have 2 or 3 piles, we'll just XOR them together, because everything we did with regular Nim carries over here, because it has all those conditions. Okay, if it's empty, yeah, you win already. And if there's 1, all you can really do is take the 1 away. 2, well, you can split it into 2 1s. The XOR, but that's the only split you could do. And the XOR of 2 1s happens to be 0. So you don't have 0, and you can go to 0 here, and you can go to 1 here, so you're at 2. 3, similarly, you can go to 0, 1 or 2, and you could split it into 2 or 1. Now the XOR of 2 and 1 turns out to be 3. Okay, so you can't have a 3, and in fact the answer is 4. Okay, so looking at 4, well, maybe you can do, you can go to 0, 1, or 2, or 4. What about 3? Well, you could split into 1 and 3. That's always 2. And you can split into 2 and 2. That's always actually 0, so 4 is 3. And we continue down like this. 5 turns out, and 6 turn out to be 5 and 6. 7 and 8 turn out to be flipped around as well. And, well, I'll continue in part 2.